This integral contains logarithmic powers nested inside trigonometric functions. Direct integration is inefficient. We simplify the structure first by applying the logarithmic property. Natural log of a to the b equals b times natural log of a. Applying this property, ln x to the fifth becomes 5 ln x, and ln x cubed becomes 3 ln x. The integrand now features ln x as a common term. Both trigonometric functions are expressed in terms of the same variable. This shared structure indicates that a substitution is the next step. We substitute u equals ln x. This implies x equals e to the u, and applying the differential gives dx equals e to the u du. Differentiating both sides of x equals e to the u gives the differential dx. The limits of integration must also be transformed. For the upper limit, e to the pi over 2 became pi over 2. The integral is now expressed entirely in terms of u. This form features trigonometric and exponential functions. This expression contains 3 distinct functions in product form. We must apply identities to separate these terms. To integrate the product of sine and cosine, we use the product to sum identity. It converts a product into an equivalent summation. By setting a equals 3u and b equals 5u, we obtain sine 8u and sine of negative 2u. Using the odd function property of sine, sine of negative 2u becomes minus sine of 2u. The integral is now a linear combination of 2 terms. To prove this identity, we use integration by parts. Let's start with the integral j. We choose w as sine ku and differentiate it to find dw. Next, we set dv as e to the u du and integrate to find v. Applying the integration by parts formula once yields this expression. We now apply the same technique to the new integral. We select w as cosine ku and differentiate. Just like before, dv is e to the u du, which integrates to e to the u. Substituting the second result back into our equation gives us this expanded form. Notice that the original integral j has reappeared on the right side. Distributing the k constant reveals an algebraic equation in terms of j. We move the k squared j term to the left side and factor out j. Finally, dividing both sides by the quantity 1 plus k squared gives us our general identity. The remaining integrals can be evaluated using the general identity we just proved. This formula applies to exponentials multiplied by trigonometric functions, providing a direct route to the solution. For the first term, k equals 8. Substituting this into the formula yields 65 in the denominator. Evaluating at the limits, the sine terms are 0 and the cosine terms are 1. The value for this part is minus 8 over 65 times the exponential difference. Similarly, for k equals 2, the sine terms are 0 and the cosine terms are minus 1. Evaluating these limits is the final step before assembly. We now evaluate the second integral for k equals 2. Using our identity, the denominator becomes 1 squared plus 2 squared. This simplifies to 1/5 outside the brackets. Evaluating at the limits, the sine terms vanish while the cosine terms contribute too. The final result for I2 is 2/5 of the exponential difference. We can now combine this with our previous result. We now combine these results according to the plan derived from the product to sum identity. Combining the fractions gives minus 34 over 65. Multiplying by the 1/2 constant yields a compact result in terms of the exponential difference. Expanding this back into the full expression gives our final generalized answer. The initial logarithmic trigonometric form was reduced to a definite numerical value through systematic application of identities. Want to see more integrals? Subscribe to Matilda Academy.